Today's webinar will deal with lead optimization using free energy perturbations, and I will be describing some of the technology, the background, and focusing mostly today on the applications of these free energy calculations that we've performed in the context of drug discovery. So just to put this in some context, FEP is obviously not the only tool available for doing lead optimization using computational techniques. There are others as well. Those would fall broadly into two categories, either a ligand-based approach or a structure-based approach. Ligand-based approaches could be types of calculations like pharmacophore modeling or QSAR. Those can be very powerful, but they do require a good amount of knowledge to be available about the active compounds for a given target. And because of the fact that they are better for interpolation among this data and not extrapolation into new chemical space, they have a limited ability to find truly new molecules that can bind to a given target. As opposed to ligand-based techniques, there are certainly structure-based techniques other than FEP. Those are mostly based on docking or other empirical scoring functions that are used to quickly estimate the affinity of a small molecule for a protein. Those can be very useful, for example, in virtual screening. But for lead optimization, they have limited applicability because they are approximating much of the key physics that's going on in a binding event. And some of this key physics has to do with sampling, which is obviously inadequately performed in a quick docking-based experiment. Free energy calculations, on the other hand, are methods that, in principle, can rigorously compute the physics of binding, and free energy perturbation is one implementation of a free energy calculation. What we're trying to do here is to calculate the free energy difference between two ligands. Here we have, that's not showing up in this particular simulation, but there's an animation that's supposed to show up where this toluene molecule is transformed into a benzylic sulfonamide. The energy difference between these two ligands is calculated by running a molecular dynamics simulation in which we are slowly transforming molecule A into molecule B. And if the model of this system is accurate and during the course of the simulation the system thoroughly explores all the important conformations of both the complexes, then in principle, if the force field is correct, the FEP algorithm will correctly compute both the enthalpy and entropy changes from going from molecule A to molecule B, which will return the correct free energy difference between these two compounds to the user. And I have to point out that we are interested in free energy differences, not necessarily absolute free energies. You can argue that the calculation of free energy differences is all you need to know if you're trying to optimize a compound for potency or for some other application. I'm going to go over some of the technology that underlies our FEP implementation, but for more information I would refer you to last year's seminar by my colleague Woody Sherman. You can go to the seminar center at Schrodinger.com, and in the summer 2015 menu you will find his recording, which you can revisit and also download the slides for your own use. FEP has been around for many decades. This is not anything new in terms of the physics. However, effective implementation of free energy calculations in practical drug discovery have been traditionally difficult because of many factors. The main factor is because these calculations are computationally very expensive. You need to do these simulations in the presence of water. Many configurations of the systems must be sampled, so you need to sample for quite a bit of time, and this has traditionally been difficult. In addition, force fields that can describe the interactions of small molecules with proteins and that cover the full medicinal chemical space were previously unavailable, and this is something that we've spent a lot of time on as well. And even if those things were covered, it still was difficult to do these things practically, because setting up an FEP job with the right parameters and the right sampling strategy was very time-consuming, required a high degree of expertise. Basically, you needed a PhD in computational chemistry or some related field, and this was severely limiting the application of this technology within within the industry. Because of these limitations, it has not been possible to do a large-scale validation across multiple targets, many different ligands. There's certainly anecdotal evidence or anecdotal reports of the success of FEP in a handful of cases in the literature going back a number of years, but no large-scale validation was published before. The issue of speed has been addressed for us by the gradual increase in power of computers, and especially the advent of GPU computing, graphical processing units, has provided us with a tool that can boost performance of these calculations significantly. So these are dedicated processors that are usually used for graphics processing, but they luckily are extremely suitable for doing molecular dynamics integrations as well. So all of our calculations are currently done on dedicated GPU hardware. Another trick to speed up these calculations is to do local heating of specific important parts of the system. You can think of the ligand itself, amino acids that interact with the ligand, and you can increase the amount of sampling and cross over barriers that would not be accessible at room temperature by injecting certain energy in the form of temperature so that these conformations can escape into another local minima or a global minima. I mentioned the force field. Many of you might have already heard of the OPLS-2 force field that was published a number of years ago, where we generated an extraordinarily large number of torsional parameters for that would cover the vast majority of medicinal chemical drug-like space. We're talking close to 10,000 torsions. The current iteration of the OPLS force field is OPLS-3. In the new version, we have also completely refit our protein force field to make our simulations better behaved at very long time scales. And you can see here on the right a little plot that shows you the performance of OPLS-3 in very long simulations for a number of key benchmarking systems in its comparison to JARM-22, which is sort of a state-of-the-art protein simulation force field. OPLS-3 does very well in predicting solvation-free energies, and that's shown here on the left. And there's a paper in JCTC from a number of years ago where we've shown that having better force field parameters makes a difference there. But we continue to improve our force field by addressing additional physical phenomena like these off-center charges that you can see in aromatic halogens and aromatic nitrogens. And we represent those in the forms of sigma holes. That's also part of the OPLS-3 force field. There's now an OPLS paper that came out this year in the Journal of Chemical Theory and Computation, and I invite you to have a look at it if you're interested in more of the background of our force field. I will have to point out that we have not covered all drug-like chemical space. Obviously, that would be impossible to have a complete coverage. We're close, but for those parameters that are not adequately covered by our force field, we make available a very easy-to-use tool to parameterize those torsions based on QM calculations, and those get automatically integrated into the force field and can be used in FEP calculations. So that's all about the methodology and the algorithm. FEP Plus is more than just an algorithm. We like to think of it as a solution. A solution would have to be easy to use, be rigorous, and we have indeed spent a lot of time developing automated setup tools and analysis tools to make these FEP calculations tractable. So what you're seeing here in this picture is a representation of a number of FEP calculations that are going to be performed for this subset of ligands. And for each of these ligands, we're performing multiple calculations. So this is compound 29 on the top left. That's going to be changed into compound 34 and compound 37 and compound 27. So for each of these compounds, we're doing multiple calculations. And this is important because of these multiple calculations or these cycles, we can do error estimates. We can assess which of the calculations are likely to be correct and which ones are likely to have some problems associated with them. This is because all of these calculations are based on thermodynamics, and if you sum over various thermodynamics parameters and go from state A and return back to a given state, the resulting sum of the free energy should be zero. So if I sum of the energy the difference in free energy between compound 2S to P and to O to O and this reference compounds and then back to S, it should, if the sampling was perfect and the force field had no random or intrinsic errors associated with them, the net result of this calculation should be 0. And deviations from this 0 point can point us to problems with our calculations, and we have various ways of remedying these, for example, unconverged perturbations by either extending the sampling or changing the force field parameters, for example. We also focused on analysis tools, so as part of our the output from a free energy perturbation, you can now visualize the torsional angles of ligands that are sampled throughout the simulation, and this can be quite important both for the interpretation of predicted free energy, so why a given compound may or may not be more potent than the other, but it can also help you diagnose certain errors. For example, in asymmetrically substituted aromatic groups, you have to start in a certain position with your asymmetric substituents, and that may not be the correct starting point. And in select cases, it can happen that the sampling is not able to rotate the molecule, that functional group, into the right position. And this is something that can be easily diagnosed from these torsional plots here. So at the end of the day, is it just a matter of setting up the calculation, doing the sampling, the scoring, and performing the analysis? Obviously not. You need to make sure that you're having the correct experimental design. We spend a lot of time making sure that our protein and ligands are adequately prepared, and we have automated tools that you may already be familiar with in the form of the preparation wizard. That also includes the accurate assignment of tautomeric states for both the ligand and the protein. We take care in the placement of water molecules. These simulations are relatively short. We're talking about 5 nanoseconds times 12, so 60 nanoseconds of cumulative simulation time, and that may not be sufficient to get water molecules in all the right places in the binding site. Importantly, you need to make sure that you're simulating the right thing. So if you have cofactors that are important for the affinity of your small molecule, those need to be included. Ions or coordinating metals need to be there. And importantly, your simulation system needs to have relevance. That is, the assay with which you're comparing your free energy differences needs to be comparable to the protein that you're simulating. And in the case of proteins that are regulated by other proteins or by cofactors or by additional phosphorylation events, for example, that may not also always be the case. Finally, it's always a good idea to go to the raw data and the protein data bank, look at the electron density, and make sure that your starting configuration is consistent, because it's well known that there are, in a large number of cases, significant errors in the PDB. So given all that, how well is the algorithm currently performing? We've applied this to an extraordinarily large number of compounds. I think the number stands at over 10,000 at the moment. And this covers both retrospective and prospective applications across a large number of targets, including kinases, proteases, GPCRs, protein-protein interactions, and fragments. Cumulatively, we can say that the accuracy of the FEP algorithm is about 1 kcal per mole for a given perturbation. So if you predict molecule A versus molecule B, you predict that free energy difference within, on average, 1 kcal per mole difference. To put that in perspective, the average experimental error associated with an affinity measurement is probably on the order of half a kcal per mole. So this is getting pretty close to that experimental error. Obviously, it would have been impossible to simulate 10,000 compounds using a manual setup. So the availability of an automated system is helpful because it improves the throughput that is necessary to impact drug discovery projects using FEP. It also makes sure that these calculations are all done in a consistent, comparable manner by reducing the ability of ourselves to make mistakes. And importantly, because the setup is relatively easy compared to what it used to be, we believe that FEP can now be safely used by people that do not necessarily have a strong background in molecular simulations or statistical mechanics. And that would be, of course, people that work in experimental laboratories. You can see or revisit or have a closer look at a subset of this validation in our recent JAX publications, where we've reported both retrospectively and prospectively the accuracy of a prediction across 10 different targets with about 200 ligands total. And prospectively, we've been able to show that using FEP can significantly improve the ability of making more potent compounds than making these compounds in the absence of using FEP. And I'll get to more prospective examples in the second half of this talk. The JAX paper covers 10 targets. Those are standard globular proteins using drug-like molecules. We've expanded our scope of validation to other domains of applicability as well. Fragments would be one of them. FEP is a physics-based method, so in principle it doesn't care about the size of the molecule, whether you are mutating an R group or a fragment or an amino acid side chain on a protein. In principle, the free energy calculations, the theory behind FEP is the same. But people do talk about fragments as if they are a different class of problem than drug-like or lead-like small molecules. And arguments for that is that most of these fragments are relatively weak binders, and since we're doing MD simulations, it's possible that these weak binders may or may not stay in the binding site over the course of the simulation. And there's the issue of degeneracy of binding modes, so fragments can adopt different binding modes much more easily than small molecules do when you make very small changes to them. For example, changing a nitrogen to a carbon in an aromatic ring. And this may or may not be captured by the molecular dynamics in FEP. We published this data, this retrospective data, in a recent JCIM paper that's listed here. The fragments data set that we looked at covered 8 different targets with a total number of fragments of 96. All of this was high-quality binding data and high-quality crystal structures, and I cannot reiterate this enough. The data needs to be representative, and it needs to be of good quality. And the data set contained both well-established test systems, like lysozyme, for example, but also pharmaceutically relevant targets like HSP90 or P38. The cumulative results look very similar to what you would expect based on our experiences with drug-like molecules, so we can draw very nice R-squared plots. And if we look at the individual data points, the RMSE, the root mean square error in kcals per mole spans the range of very, very good, like MUP, where we have an RMSE of 0.4, to acceptable for P38 and slightly less good for HSP90. But what's important is that we get the correct sign about 90% of the time. What that means is that if we compare two compounds with one another, in 90% of the time we can pick out which one is the most potent. The average RMSE is very close to 1, which was the overall RMSE for all of the 10,000 compounds that we looked at. And the R-squareds are generally good as well. Obviously, R-squareds depend a little bit on the potency range that you're looking at and the number of compounds that you have, but these are all pretty acceptable values. For this particular study, we've also been able to look at a comparison of FEP generated results with other computational tools that we have, like the glide docking score or 2 variants of the MMGBSA algorithm, which is another widely used tool for structure-based lead optimization. And it's certainly true that in a number of cases, both glide and MMGBSA do a fine job, for example, MUP here. But there are many, many cases as well in which both methods completely break down, and there's absolutely no correspondence between the predicted values and the experimental values. Whereas FEP across the board gives acceptable results for all data sets. Another domain of applicability that we've studied are membrane proteins in the form of GPCRs. Here, the simulations have to be done in the presence of the membrane, which slightly complicates the automated setup, so we spent some time hammering out the details there. This has been done in a collaboration with a group in the Netherlands. We've looked at 4 data sets here: the beta receptor, the A2A receptor, the delta opioid, and the CXCR4. And cumulatively, the results look when you separate cumulatively, the results look very similar, again, to what we've seen for the fragments and the globular drug-like proteins as well. And if we look at the individual data sets, we again see acceptable MUEs, good R-squareds when it's possible to actually calculate an R-square for all of these targets. So I'd like to conclude from the first part of this talk that if you have good quality data available, that means both accurate assays and good crystal structure data, and you are asking the methodology the right questions, so the similarity of the investigated compound space must be reasonable. All of these compounds must be congeneric. We have a sort of a rule of thumb that we cannot perturb between compounds that differ by more than 10 atoms. So that sort of limits the amount of chemical space that you can sample within a given FEP calculation. But if those criteria hold, then FEP can give you very reasonable affinity predictions with an average error of about 1 kcal per mole, which we would argue is highly useful for prospective application in drug discovery. Which is what I will be talking about in the remainder of the talk. I'll go over 4 projects in which scientists at Schrödinger have been able to support experimental collaborators in other companies using free energy calculations. The first collaboration that I want to describe is what we've internally called Collaboration E, where we've been able to identify a new potency driving R group on a small molecule, and also have made some direct comparisons to traditional approaches, which include both, I will get to that in a second. So the issue at hand here was a compound with 800 nanomolar affinity. This is a sulfonamide, an aromatic sulfonamide. And the customer was, our collaborator was interested in generating, improving this potency. And it turned out that we were able to fairly rapidly make a number of analogs based on a library of available sulfonyl chlorides, about 250 compounds. We had a variation of selection strategies that were used to actually pick out those compounds from those 250 available reagents. 5 compounds were made simply because they were very easy. 7 compounds were made by docking these molecules into the protein structure and looking at the interactions that the ligand could form with the protein, basically an inspection of the 3D fit without taking into account FEP data. And then there were 8 compounds that were made based on prioritization by FEP calculations. The signal is very clear. All of the compounds that were made by FEP have good potency, in many cases better than, in all cases better than the lead compound. The docking-based or visual inspection-based compounds are in some cases very close to the affinity of the initial lead, but in some cases are dead. And those compounds that were more or less picked based on ease of use or synthetic tractability, in all cases did not improve the situation. So this is an example where FEP was able to advance a project with significantly more potent inhibitors. And here you can see what those inhibitors look like that were made based on FEP. You can see a variety of aromatic systems here, and I would argue that these are not compounds that you would stumble upon randomly. There's a lot of variation here, and a lot of these are not simple, trivial substitutions on this heterocycle where we're hopping a few halogens around. No, these are quite substantially different aromatic systems that would not be easy to pick out by hand. The next collaboration is illustrative of how FEP can be useful when you're doing simultaneous optimization of multiple parameters. And for example, these could be, in addition to potency, selectivity of your compounds for other targets, and also solubility, which is something that we can address with FEP. I'm not going over the methodology in any detail, but we do have a tool to predict solubility with free energy perturbation as well. And the problem here is that this collaborator had a molecule that was highly potent, and it had the right selectivity, but it was poorly soluble, which made it impossible to take forward into the clinic. There was another molecule that was made that addressed the solubility, but in that case they lost a very important feature, which is selectivity over target 2. That would be molecule B. And similar, molecule C had good solubility and selectivity over anti-target 2, but did not prevent binding to target 1. And then there was molecule D, which had neither selectivity for target 1 and had poor solubility. We screened a very large number of idea molecules using FEP and synthesized a whole bunch of them over the course of a number of months. And we were able to find 2 compounds that matched all of the 4 criteria that were necessary to take these compounds forward. And just to show you what type of changes were necessary to make these compounds fit all criteria, the start was molecule D here, so the core was attached to a morpholino R group. Molecule E had a pyrazine with a extracyclic carbon and a hydroxyl group. But the most interesting compound was probably molecule F, where we have a seemingly trivial change, making a morpholino group 1 atom bigger by adding a 7th atom in the ring. And this dramatically improves solubility while keeping both potency and selectivity at an acceptable level. And this is one example of where if you were to make a morpholino ring, it would be very hard to imagine that the next proposed compound to remedy the solubility and selectivity issue would be a 7-membered ring with a nitrogen and an oxygen. And you really need a tool like FEP that can give you quantitatively accurate results to suggest these types of changes. The third collaboration that I want to mention here is has to do with an example where we were able to very rapidly optimize the potency of a compound for a target using very few compounds. The starting point for this project was a virtual screen. We had a lead molecule from a virtual screen calculation where we had a 2 micromolar affinity for a target. The initial round of optimization was done in 2 stages. So we used water map, calculation of hydration sites in the protein to suggest where substitutions on our lead compound might result in affinity changes, and then using FEP to actually prioritize those designs for synthesis. The first round of optimization, we made 4 compounds, and the affinity of the compound was reduced from 2 micromolar to 82 nanomolar, or was improved rather. The second round of optimization included a larger number of compounds and was able to drive the potency even better to 14 nanomolar. So this is an example of how you can take a hit from a virtual screen from a low nanomolar compound, from a low micromolar compound to a low nanomolar compound in a very, very small number of compounds. In this case, 14 synthesized compounds were needed to achieve this almost 100-fold, more than 100-fold improvement in potency. But the final example of a collaboration that I want to go over is collaboration B. The collaborator here was interested in developing a weak binding compound for this particular target. The IC50 that was measured was 6.9 or 10 micromolar. 100 nanomolar, sorry. The amide chemistry associated with making this compound made it fairly easy to consider alternatives to this hydrophobic cyclobutyl group in part of the core. There were a number of possible compounds that were able to be synthesized based on the available reagents, and FEP was used to rank order these compounds. These included small hydrophobic rings like the cyclopentyl or cyclopropyl with various hydrophobic substituents on them. And FEP was in fact very, very accurate in predicting that none of these compounds were actually much more accurate. So the compounds were synthesized despite the fact that FEP indicated that potency was not necessarily going to be any better. So that is a satisfying result from a computational point of view, but not a very satisfying result from a project point of view. So the collaborator wanted to know if we could suggest anything better based on additional FEP calculations. So we took an amide coupling library from a commercially available vendor. These building blocks were used to generate 248 possible compounds that were docked into the protein using Glide. And then following some manual inspection of poses, 22 compounds were selected for FEP analysis. These 22 compounds were reasonably diverse and not only hydrophobic as shown on the previous slide, and they include these various changes here. the only compound of the two that were predicted and that was predicted to be better was this cyclic carbamide shown here, where FEP predicted it to be half a log unit better than the reference compound. Now, based on the observed FTR of all the other compounds and the crystal structure of this small molecule, the collaborators were deeply skeptical that this prediction was actually accurate. Nonetheless, they did agree to synthesize it. And they had very good reasons to be skeptical. If you look at the crystal structure of this cyclobutyl, there's really no obvious hydrogen bonding opportunities for a polar group to engage in with the protein, and so the prediction that the cyclic carbamate was active was non-intuitive. If you look at what is going on during the FEP calculation, now remember these are molecular dynamics simulations-based calculations, and they take into account the flexibility of the protein. And what's important here is that it allows the protein to reorganize around a new R group that's introduced in the protein binding site. So the starting position of the calculation was something like this, but at the end of the calculation, what's actually being formed is that a direct hydrogen bond of the heterocycle with these two amino acids that form a salt hydrogen bond in the crystal structure of the cyclobutyl group. Obviously, this is not something you could detect using a docking algorithm because that assumes a rigid receptor structure, and even in something like MMGBSA, it's not typical to observe these types of conformational changes. I want to show a few slides of work that has been done by others using the FEP technology. There's a number of groups throughout the world that are now using this technology quite substantially in driving projects forward if there is a structural basis to do so. This is an example from Janssen Pharmaceuticals that was presented at our user group meeting a year ago in Paris, where they applied FEP to several hundreds of compounds and were able to get a fairly good rank ordering for a number of those compounds, and found one compound in this arylic heterocyclic class that had 1 log unit better activity than the reference compound, and was able to deliver a very interesting lead with improved properties. Here's another presented result by AstraZeneca. This was done already 2 years ago at the CCP Biosim conference. They did both retrospective and prospective validation across a very large number of targets, and a small number of targets, but with a very large number of ligands, and got RMSE values that were very comparable to what we've been able to generate internally. That's always important to do. Obviously, as a computational chemistry company, we validate our methods rigorously, and we're very happy to see that prospective applications with our collaborators result in usable results. But external validation by third parties independently of what we're doing ourselves is also very important. Right, so that's where FEP is standing at the moment. Just in the last few minutes or so, I want to go over what's to be expected and what is available in our new release. The 15.4 release, which was released about 4 months ago, and the 16.1 release that was released a number of weeks ago, we've addressed some new issues. Desmond has become significantly faster compared to 15-3, so it's about 2 times more effective than it used to be. As I mentioned, we have tools to automatically detect which calculations are not converged, and where you have to make sure that either your torsion parameters or your force field parameters are correct, or something else is not going on with your simulation that's producing an error. We are providing back-end support for doing FEP with covalent ligands. We are able to do calculations both for protein stability and for protein-protein interactions, so the effect of mutagenesis on affinity of one protein for the other, and the effect of mutagenesis on the stability of a protein in solution. And I'll briefly go over the FEP scanning panel as well in the next slide. In 16.1, we now have the ability to measure or to expose these ligand torsional profiles that are sampled throughout these simulations, and I showed you that at the beginning of the talk, and some advanced settings to enhance sampling for multiple binding poses, which perhaps could address some of the simulations that don't converge. The FEP scanning tool is sort of a simple version of our FEP tool that very quickly does a number of calculations. The turnaround is quite fast, about 1 hour per compound on a GPU. This is about 12 to 24 times as fast as a rigorous FEP calculation, which takes about a day on a GPU. Now, even though these calculations are quick, they are accurate because the changes that we're making here are fairly small. So we're introducing single atom substitutions on a ring, for example, a methyl or a hydroxyl or an amine or a halogen, or substituting carbons for nitrogens in this nitrogen walking exercise. The suggested use of a tool like this is that you generate a very large number of possible derivatives from your compound automatically, and then perhaps select the 5 or 10 most promising candidates and validate them using using the standard long time scale FEP calculations in a second round of calculations. Here's some validation on 3 different data sets. The protein PDB is listed in the second column. The number of idea generations, this is all for methyl scanning, so different compounds that differ by a single methyl from the reference compound. And then we rank order those compounds and ask whether the compound is able to pick out the methyl substitution that has the largest improvement of potency. So these are the so-called magic methyl substitutions, where adding a single atom to a single carbon to a compound can lead to a drastic improvement of potency. Now, in 5 of these 6 cases, the method was able to pick out which of those magic methyls was, in fact, the correct one. Actually, PI3K is a counterexample where the methyl at the identified position is actually leading to a decrease in potency. As I mentioned, we have backend support for covalent inhibitors as well. The binding data here pertains to reversible covalent inhibitors, so the thermodynamic property is not the kinetic property. And this is important because it allows you only to calculate the correct thermodynamic property for ligands that have the same warhead. Stay tuned for additional publications coming online in the next couple of months or so. We have presented our work on protein-protein binding and protein stability binding and antibody-antigen binding at various conferences over the last couple of months, and we're currently preparing publications here. And the same goes with FEP on homology models. I'm not talking about that at all today, but we have been able to show that you can run FEP using homology models if your homology model is reasonably similar to your crystal structure. And that should be out pretty soon as well. In future releases, we hope to address core hopping, so the making and breaking of bonds in rings, which is extremely powerful because it will address a long-standing problem in the medicinal chemistry, which is swapping of cores. Those are usually complicated synthetic problems to solve, and if we can address that computationally, that would be very valuable as well. And I mentioned briefly that we take great care of making sure that the water molecules in the protein binding site are correctly placed, and we are currently trying to implement Grand Canonical Monte Carlo to have some form of adaptive water sampling during the course of an FEP simulation. None of this work would be possible with the development team that makes sure that this science is actually implemented into a piece of software that can be used by us and by people in the field. Robert Abel is the leader of that team. All of my colleagues in application science and the drug discovery unit work very hard to make sure that these programs are validated and all of the prospective applications as well. Rami and Rich are the founder and the president of the company, not in that order. And then we have a large number of scientific advisors that have been pioneers in the field of free energy perturbation that have helped us over the course of the last few years, making sure that we have a tool that's both scientifically sound and practically usable. So with that, I would like to break and would be happy to take some questions from the attendees.